Okay. All right, here's part 2 of chapter 3, of chapter 2, I should say. I'm dealing with kinematic motion. And I'll finish up, start off where we finished up last time, our equations of motion for x direction and for y direction. And we'll look at a couple examples here in each case, all right? So I'm going to leave this up as far as the equations, but we'll do a couple examples. So one thing might be, if I have a car with an initial velocity of 0 and acceleration of 5 meters per second squared. All right, question would be, what is v and x after t equals 5 seconds? Okay, so here's the problem. So what we have here, all right, we have v0, v0 is 0, a is that, and t is, what is that? What are v and x after that point? All right, so I'll move these over to here. So v0 is 0, a is 5 meters per second squared. All right, so we're going to find at, and then, after t is 5 seconds. All right, first case, v would be v0, which would be 0 plus 5 times 5, which would be 25 meters per second. All right, that would be the case there. For x, we'll take x0 to be 0, so that would be 0 plus 0 plus 1/2 times 5 times 5 squared. That would be 25, that would be 62.5 meters. All right, so notice how it would, after 5 seconds, it's gone 62.5 meters. So that's an example there of what we're trying to find given numbers. We're not going to use the second equation, the third one, because what we're trying to do is find v and x based on acceleration and a time. All right, so that's the first example. All right. Here's an example that might work, right? It's an example of a runway aircraft carrier design, and it has a certain length, x. And the question is, it starts from 0, v0 is 0, and for it to take off, the velocity must be 30 meters per second. 30 meters per second. And it can accelerate with an acceleration of 2 meters per second squared. Well, let's change it. Let's make it something different. That's not that big a deal. 5 meters per second squared, so half a g. All right, how long does it need to be, which is 30 minutes, just about 70 miles per hour. Actually, that's probably on the low side. Let's make it 50 meters per second. So it needs a speed of 50 meters per second and accelerates at 5 meters per second squared. How long does it need to be so that when the plane reaches the end, it'll actually take off? Understand the problem? Starts from rest, accelerates at a constant acceleration. At this point, v is 50 meters per second. If we are long, with the accelerator, how long does it need to be? And the question is, you might say, well, what does that got to do with it? Well, x, this would also be x naught is 0, because as we'll see, the longer it is for its acceleration, the faster it's going to go at the end. So what do we know here? We're trying to find, in this case, x. So we have v squared is v naught squared plus 2ax. So that would be v squared is 0 plus 2ax. So that is 50 squared equals 2 times 5 times x. That would be 2,500 divided by 10, which would be 250 meters. All right, which would be aircraft carrier, 250 meters, that's almost 800 feet long. That seems a little on the long side to have to be that quick. So maybe we, that's a very long one. So let's try something different, all right? So for that parameters, it would be 250 meters in length. All right, so instead of that, let's try acceleration of equivalent of 1g of 10 meters per second squared. How long does it need to be then? All right, v squared is v naught squared, which is 0, plus 2ax. So that'd be 2,500, because we still need that speed. 2 times 10 times x. So that'd be 2,500 over 20. That would be 125 meters, which is probably more doable. All right. Now 50 meters per second is about 125 miles per hour. So that's a realistic speed for it to take off, to have that. Now it'll go once it gets going, but it has to be 125 meters in length for that to occur. Well, this is where you use the bottom equation because we are trying to solve for x or a given x. In the problems where you're not worried about time, but you're worried about position, then this one is where it's going to be more important. All right, so moving on. We're going to go into free fall. So let's move on to our equations on the right. And I will use this instead. An example might be free fall. And this is where we had Galileo, which is an example of dropping objects from the Leaning Tower of Pisa, which he may or may not have done. I mean, he's claimed he did. And as he noticed, as the object drops, after 1 second, it's fallen 4.9 meters. After 2 seconds, fallen 19.6. After 3 seconds, it's fallen 44.1 meters. So for free fall, the graph is going to look like that. So we have initial velocity of 0, and the graph of y versus t is going to be a parabola. All right, so in this case, if we have strictly free fall, then the simplest case here is if v naught is 0, then y is 1/2 gt squared. Simple case. All right? So basically it goes as the square of the time. All right? So that's a case there. So we see after 1 second, so we plug in at t goes 1 second. Y would be 4.9 meters. 2 seconds, y would be 19.6 meters. And 3 seconds, y is 44.1 meters. All right, if we use g is minus 9.8. Now in this case, since we're just dropping it downwards, I mean technically these should be negative, right? Because we'd be starting from 0 and going downwards. It's like going down into a tunnel, into a well. So this would be, and this would be the graph we'd see here, right? So that's free fall for that case. All right. Now we can also see is if you drop an object and let it fall, and you time how long it takes for it to fall, you can tell how deep it is. So if it takes 1 second, it's about 5 meters, which is about 18 feet. If it takes 2 seconds, about 20 meters, that's about 35 feet. So the time it takes, if you drop something into a well, time how long it takes, that'll tell you how far down it is in that case. All right. Now, moving on, a little more complicated situations. Let me try one here where we're not just dropping it. Here, in this case, V0 is 0, and we're taking Y0 as 0, all right? So we just drop it, and then we get the kind of graph. Let's do something a little different. 2 different cases. You know, we can start at a point of, you know, Y0 is 0. Right? And we can throw it upwards with a velocity of 10 meters per second, or we can throw it downwards with a velocity of 10 meters, minus 10 meters per second. And the question would be, what would be its position? In this case, let's say t is 2 seconds. What would be the case here, y? And what would be the case y here? Right? Velocity is the same number, throwing at 10 meters per second. In the first case, I'm throwing upwards. Second case, throwing downwards. What would be the position after 2 seconds for each one? Interesting problem here. Now, if you do look at it intuitively, what's going to happen is, in the first case, it's going to go up, it's going to slow down and stop. It'll stop after a certain amount of time, and then start going back down again. First case, in the second case, you throw it down, all it's going to do is get faster and faster and faster. So we're going to use g is minus 10 meters per second squared, just to make solving the problem easier. We could do it multiples of 9.8. So let's look at the graph here for these cases of what the velocity would be for each case. So if we start with, this would be the top one, this is the bottom one, all right? If we have 0, right? In the first case, this is up, down. In this first case, we would solve for the time, position, all right? So that would be V is V0 plus GT. That would be 10 plus negative 10 times 0, which would be 10 meters per second. So I'm going to drop the units because the units will be in meters per second. So this would be plus 10, and this would be minus 10. Okay. So units in meters per second. Now let's do 1 second. This would be 1. This would be 10 plus negative 10 times 1. That would be 0. All right, so for the first case, t equals 1 second. That would be 0. And for the other case, that would be minus 10 times plus negative, that would be negative 20 meters per second. All right, now let's say after 2 seconds, that's our next case. For 2 seconds, for the first case, that would be 10 plus negative 10 times 2, that would be 10 minus 20, which would be minus 10 meters per second. So for 2 seconds, that would be minus 10. And for the other one, it would start minus 10 minus 10, that would be minus 30 meters per second. So notice how this is getting bigger, and this one is, so if it kept going on, this would be minus 20, this would be minus 40, and so on. So if we were to do a graph of this, and I'm gonna erase this for now because that's what we're looking at. To get a graph of the position of that, then what we would have is, in the first case, V naught, so this is T, at T equals 0, so this would be 1, 2, 3. This would be 10, and at T equals 1 second, it'd be 0. At T equals 2 seconds, it'd be minus 10. As T equals 3 seconds, it'd be minus 20. All right? So here, velocity, the velocity is 0 at this point. For the other one, start at T is minus 10. At the next one, it'd be down there, and down there. Notice how they're both shifted only by the initial velocity. And in both cases, the slope would be g, minus 10 meters per second squared. All right? And in the first case, it stopped when it reaches the top, when it crosses this axis here. The other one never slows down. It just gets faster and faster going down. But they're all, both of them have that concept there. So this would be the plot of velocity versus time as far as that's concerned. If we were to plot position versus time, it would look something like this. Where it would go, or let's say y, since that's reply, it would be something like this, where at its peak, this is v is 0, and then it goes faster and faster until it reaches the bottom or whatever. So this would be position versus time. This is velocity versus time. So be careful with those equations as far as that's concerned, because in here, velocity is constant and it's minus 9.8. You're not going to have any kind of kink where it's that case. All right, last thing here, and we'll look at some example, just the last section here, as far as that's concerned. So we have our equations, and you can do some problems. Okay, we'll have the homework problems. But again, if we plot x versus time, then if we do this kind of case, all right, then the slope at any given point is the velocity. So here the velocity is changing. And if we actually were to try to attempt velocity versus time for this sort of graph, here it's very small. Then it starts to rise and then peak again. So it's rising gets less than, let's see, then the velocity becomes negative. Well, let's see. That's a good question. Here the velocity would be high, positive, and here the velocity is positive, here velocity is negative. And at this point, this is where the velocity is 0. So in this case, it would be, to plot velocity versus time, it would be going high, slowing down, slowing down, slowing down, and then becomes negative. All right. So that's some of the examples. They've got some problems related to that in the text, but this is the introduction to chapter 2 as far as position versus time, and we'll have some of the lab questions related to that, problems related to that. All right. So again, this is chapter 2. I'll start next time on chapter 3.